off and sharing my screen. Now, it worked before. We'll see if it works now. Okay, you should see a slide that says QKD and mine and Bob's name. Are we all good?
You are good.
Good.
Fantastic. All right, so hey, I'm Alice. And we got Bob here. And I'm a high school physics teacher who's done a bunch of work with the Quantum for All project, trying to get quantum into the high school classroom. And I've been teaching for like 30 something years. And Bob can introduce himself.
I'm now retired from my Associate Executive Officer position at AAPT. Over the years, I've taught physics at a number of colleges and universities across the country. And last fall, I taught a course at the University of Maryland in College Park, introducing quantum computing and some quantum physics to computer science, computer engineers, and math majors. That was a lot of fun, but that led to yet another book, which Alice and I are just wrapping up the manuscript, and that will be off to the publisher in about 2 weeks, and will hopefully be on your wherever you buy your books early in 2026. It has a little more physics in it than the first version because of the intended audience that we were aiming for. Ups the math level just a little bit, mostly linear algebra stuff. But I think it's going to be a nice complement to the earlier book, which was really aimed at a broader, probably less mathematically sophisticated audience.
Okay. So a lot of what I'm going to be doing is going to be based on things that I've done with high schoolers or done with, I see Trina has on one of her PTRA shirts. So also things we do with the physics teacher resource agents. So that's kind of where I am, but intro physics is not necessarily very different audience than probably what I work with. So let me see if I can, it doesn't want to, there we go. So hopefully we'll get through it all. Talk a little bit about cryptography and some of the basics, some fun history, and then go on to the way we currently do internet and all security with the RSA, and then how we can break it using quantum computing, and then looking a little more in depth in using quantum cryptography, which should be unbreakable, even if we get quantum computers. All right, so one of the things that when I do this with my students and what prompted us to do it is that if we get a big enough quantum computer, we can break internet security. We can break all those algorithms. And Bob will talk later on about how difficult they are to break with a classical computer. But if we up our game with quantum computers, we can break that. So we have, I've heard it referred to as, another space race of trying to be the first country to get quantum computers. So lots of places are throwing a lot of resources at this. So basically, what is cryptography? Okay, so I don't tend to PowerPoint or talk a whole lot. So if you guys can help me out and in the chat, if you could just tell me something you see in this diagram right here. Chris, my cat is here right on time. But if in the chat, if you could tell me just one thing that you see in that diagram, that would be wonderful.
Two keys.
Okay, 2 keys. I see you need a key to encrypt. Hey, this is interesting. So I pulled up the chat. Does that show up now on your screen or no? Ooh, so it's secret. Okay. All right. So we have 2 keys. Can a couple other people write whatever they see in here? Eve in the middle. Doesn't she look like a pleasant person? Come on, kitty. No. Okay, so we got these keys. We are encrypting. We are decrypting. We're doing something with Eve. Okay, at the end, hopefully we'll see what we do with Eve. So when we were talking before this started, I was talking about how I've been sitting in this area for now 2 hours and my cats have ignored me, and how the minute that this started, the cat was going to come. And there it is. Within 2 minutes, it was like, oh, look, I should come. Okay, I will stay on task. Hello, kitty. All right, so, sorry. I'm still trying to figure out how this, hi, honey. Okay, so putting you to work. Here's an example of a cryptogram. So here is a cipher. Here is a secret message. It's a riddle and it's about weather. I gave you a couple hints down there. Take a couple minutes and see if you can figure out what the riddle is while I pet my cat. And if you get it, you can just put that you got it in the chat. Don't put the answer in the chat because we don't want to ruin it for anybody. Hey, Tom, here's a good hint for you. See that apostrophe there? That should narrow it down to a letter. Not just Tom, anybody else who needs another hint. I love it. I have the answer, but not the, oh, that's interesting. So you were able to figure out the answer. Ooh, Trina has it, maybe. We'll take about another minute. Okay, people got it. All right, Trina, you were the first. Can you tell us just what the question was? Oh, I think, are you muted? Yep, you're muted. Can we unmute you?
Okay.
There.
Oh, the whole question. What is a, oh gosh. That's the one that, the word that's giving me crazy when it's right there with the X in
Okay.
it.
Okay. Somebody else, just hop on. Tell us what you had for the question.
Okay, what is the,
Brian, you want to say what you thought the apostrophe word was?
that's
Sure.
an S
It's
on the tag.
tornadoes.
Yeah. What is the tornado's favorite game? All right. Someone want to shout out, or all of you shout out what the answer was?
Twister.
Twister. Yeah. Okay. So, curious, and there's a reason for doing this. How did you figure it out? Besides my hints. So, if you could just go ahead and unmute and just say whatever you use to figure it out, and I'll put it back up there because it may help to see it.
I figured the
Mhm.
first 3 words were what is
Yeah, because it was a riddle, right? So because you knew it was a riddle, okay. Other folks? Uh, got you. Look for common 1 and 2 letter words. Yeah, so that second word, right? And if you combine it with what Chris had says, it could be is, it could be at, right?
Oh, Twister.
Yeah,
So the answer is Twister.
yeah. So then we get the apostrophe, right?
Mhm.
Mhm.
So the whole point, come on, right, is that there's a pattern. And oh my gosh, what just happened there? Okay. Sorry, folks, I don't PowerPoint and I don't Zoom very often. The two together is going to be an annoying thing. I apologize. Right. So for the English language, here's frequency analysis. So when I do this, I give my students a lot of the cryptograms. There's a couple sites that'll generate all kinds of different quotations that have, 15 words. And a lot of them love them. They absolutely love them. And then we can go through a page if I want to perhaps torture them, and we actually do a frequency analysis. I'm sure you all don't have a chance to do that, but here is the frequency analysis for the English language. And as you would expect, right, E is the most popular. Not a whole lot of Q going on, not a whole lot of Z going on. Right? But this can also help you break the cipher. Right? You look for, especially if it's longer. If the short one I gave you is a little harder, but the longer one, right, you can start playing these tricks, the apostrophe tricks, if you know what type of question it's going to be. There are all these tricks, and there's a pattern. So, lucky for us, there was the movie Imitation Game, which a lot of people saw, a lot of our students have seen. So they tend to know about the Enigma from World War II. And now they know about Alan Turing, they know some of it. I want to show you really different tiny clips of these, with the whole point being is that there is a pattern. Okay, the last one is we're not going to show it because I'm 100% Polish and people always, make fun of Polish people. So I had to put that one in there that the Poles did it first. They had it was a less powerful, the first Enigma, but then they passed it on to the Brits and helped the Brits. So that was purely for me. So let's watch a minute of the first one. Not that. Come on. There we go. And hopefully the sound's going to come through. If it doesn't, please let me know.
There's no sound. You'll have
There is.
to you have to share sound as well, or share audio.
Is that on Zoom?
Yes,
That's a Zoom thing.
I believe so. Under advanced sharing options, maybe?
Ooh,
Nope.
interesting. Oh my goodness. Wait, now I can't even get, oh, there we go. Share. I apologize, folks.
Under advanced, there should be a computer audio.
Who can share? Who can share? Nope, I only get that one person can share. That's okay. We could skip this part, and I can give you the very short my version. So one of the things that they did was they did traffic analysis. They started looking at where messages were coming from and where they were going, and they could map out where units and battalions were based on just for the traffic. They could just do a little bit of the code and they could figure out where people were and where they were going. Find out where they're going, maybe you can figure out what they're up to. The second one is a deeper dive into what they show in the imitation game about the idea that the beginnings of the messages tended to all be the same, and the whole Heil Hitler thing, but also weather. So they knew there were some words, like Chris said about, because it was a riddle, she figured out the beginning of the riddle. Okay, so they could figure out, look for weather terms, and then the big flaw in the enigma is that a letter was never coded as itself. An S was never itself. So they could use frequency analysis of letters. Right, we have words just like, German has word with double letters. They can use all that because there was a pattern. Patterns is how you break cryptography. So perfect cryptography needs to be random, right? Q quantum, right? Quantum has that lovely element of randomness. All right, come on, move. There we go. So, and then just to get into some vocab, every cipher has a key. So here is a running cipher or a Caesar cipher. Well, all you do is you put letters for numbers, right? But the key, this would be the key. This one, based on a little bit on the geometry, this is what's known as the key. So the cipher for this one would literally just have, like the shape for an A, you would just have those two lines. If you want to have an S, you would have this V symbol. But in order to decrypt it, you need the key. So when we were first starting to teach this to teachers with Quantum for All and PTRA, there was confusion over what we were trying to figure out. You got to keep the key secret. Okay, if the message gets caught, that's fine, right? Because you can't break it unless you have the key. That whole imitation game thing, all of it is all about getting the key. Okay, what symbol or what letter or what number stands for what? So we're going to be doing quantum key distribution. The algorithms that Bob's going to talk about is going to be about getting the key, not the message. That was really a confusing part for us and even for my students at the beginning. All right, so I'm going to stop sharing and Bob's going to take it over, who I think is hopefully going to be better at manipulating it than I am.
All right, let me fire up here. Go. All right. Just one little minor thing here. All right. So in this next 15, 20 minutes or so, I'm going to walk us through one of the first modern cryptographic methodology that was developed way back in 1977, ancient history, to obviously far in advance of quantum computers, the internet, and everything else. But people had realized that in sending various communications via radio or microwaves or other mechanisms, it was important to be able to develop a cryptographic key that would be extremely difficult for an intruder to break. So that what you send would be a secure message. And this goes on in your laptops and computers in your office all the time. If you're using, for example, on the internet, you're using an HTTPS connection. The S is security, secure, and they are sending back and forth all sorts of obscure codes which carry the key and other information that's necessary to encrypt the message at one end and unencrypt it at the other end. And these things have been become very sophisticated over the years. We're going back to the beginning because it's still a little tricky, but it's mortals like us can understand these things. And I think it's a good example of the kinds of methodologies that have been adapted in a variety of different ways for modern cryptology. But as Alice pointed out, toward the end of the time, a quantum protocol which can break all of these encrypted methods of the type we'll describe. And so the question is, what do you do to, once quantum computers become more prevalent, what do you do to avoid having bad actors get onto the scene with their quantum computers and steal all your secret cat videos and things of that sort? And it is a very serious business. You may have noticed that computer science departments often now have a cybersecurity certificate or as part of their program, and hundreds of students go through those programs. And in the Washington, D.C. area, there is a consortium of colleges and universities all preparing students in the cybersecurity area dealing with these kinds of issues. Now, what we're going to be looking at, let's just make sure we keep our framework straight, is going to be a purely classical algorithm. There's no quantum things involved in it at all. And for the last part of our workshop, Alice will show you how we can invoke the magic of quantum to protect ourselves from people who might even be able to break the classical encrypting methods. So we'll get to that point toward the end. So
By the way, you mentioned cat videos, and then one of my other cats showed up right when you said cat videos. So we will talk no more about cats. There will be no discussion of
I see.
Schrodinger's cats. If
Okay.
not, you're going to get a lot more butt views. Okay,
All
I'm
right.
being quiet now.
All right. Now, when I run my cursor around, can you see it?
Yep.
You
Yeah.
can see that. Okay, good. Because on some of them, you get a little sort of a laser pointer thing, a little red dot to chase around, but apparently not on this particular setup. Okay, so let's get ourselves underway. So as Alice showed in our sort of introduction, all this encoding stuff is to set up some mechanism by which you can build a cipher message, send that, and then unencrypt it at the other end. And there are, as I mentioned, there are many variations on these kinds of things. This is the RSA one is an example of what's sometimes called public encryption. You actually don't need to keep your key completely secret, though it sometimes helps just not to have too many people have their eyes on these things. So it can be part of it can be made public, but there's part that's kept private, which makes sure that if somebody really wants to unencode the messages, doesn't have access to those parts which enable the unencryption. And it's also called asymmetric because there's one code used to encrypt and another code used to unencrypt at the other end. So that's the basic strategy of this particular encryption scheme. Now this encryption scheme, like most of the schemes still in use today, are based on properties of integers, number theory in mathematics. And I know that most of you have physics backgrounds and probably have not studied any number theory. I had not. And found some of the ways that people describe these things kind of mysterious. But once you get your head wrapped around it, there are also some really amazing mathematical ideas that pop up that really are quite interesting and puzzling. Um, and that's what makes these systems difficult to unencrypt. So we'll walk our way through some of that so you have the vocabulary for what people are talking about. And then we'll work through one numerical example so you can say that you have actually implemented the RSA cryptography system. Put that on your resume. It's not the sort of thing you would want to do. I mean, there are professionals who do this with fancy computer algorithms carrying out all the work. But it's interesting to see that if you were somehow caught on a desert island, there's some things you could do to encrypt messages by hand.
I think if I was on a desert island, I want to make like the clearest message of help I
Yeah.
possibly could, but
Well,
but maybe there's pirates around, right?
maybe, who knows? Who knows? Okay, so
Book number 3, Bob.
here we go. So buckle your seatbelts. As I mentioned, a lot of this is based on number theory and dealing with the properties of positive integers. How simple could it be? 1 + 2 is equal to 3, even in Washington, D.C. these days. And there are several parts of number theory that come into play. One of the most important is this notion of prime numbers. And you may have met this because it's often worked into algebra classes and so on in high schools. So, but just as a quick review, in number theory, a number is a prime number if it's evenly divisible only by 1, which of course divides everything, and the number itself. And divisible evenly means there are no remainders left over after you do the division. So I've got a couple of things here for you to take a look at. Of the series of numbers I've written down there, take a quick scan of those, and see which you think are prime numbers, evenly divisible only by 1 in the number itself, which are not prime numbers, and then we'll have a little collective discussion of that. So I'll give you maybe about 30 seconds to do this.
Like some people are.
And you can either put it in the chat or we'll just unmute everybody and we can talk about this collectively.
So far, we are all agreeing.
Okay.
Bob, it
Well,
looks
I'm
like
going to say that what you're doing here in terms of studying number theory, most of us have had number theory if you've had any kind of math up to calculus, especially that. So the number theory that they're starting with here, or that you're starting with here, is common to mathematics people who have studied it, not necessarily knowing they're looking at number theory.
Sure. That's absolutely right. But we'll see there's a lot of more sophisticated things that are probably not part of our traditional backgrounds in math, unless you're a mathematician and take a course in number theory. Okay, so I think we're in pretty much agreement that the 17, 2, and 79 are prime numbers. What's wrong with 15?
It's got two factors, 5 and 3.
Okay, yeah, that's all there is. What about this long thing here?
It's even, so therefore it's divisible by 2.
Yeah, Trina's really on top of it. That's great. Yes.
Reagan has an interesting trick that I had never heard of before. Sorry if I
What?
mispronounced your name.
I can't see the chat while I'm in the screen share mode. So what, go ahead and shout it out.
Oh, it's if you add up all the numbers and divide the sum by 3, like if it's divisible by 3, then the number is divisible by 3. And same with 9. So
Mhm.
that
Oh,
big number adds up to 69.
right.
So
Oh,
that's divisible by 3.
okay.
Yep.
Very good. Very nice. This is also all prime numbers, once you get beyond 2, are odd numbers. Because if you have an even number, it's divisible by 2. So it can't be prime anymore. So this is an even number, so it has to be a non-prime number. Okay. All right, let's then move along here. Now, in many of these cryptographic schemes, you deal with two quantities, two prime numbers, which are then called prime factors because you multiply them together. So if you have two prime numbers, P and Q, multiply them together to form a new number, N. This product then becomes a critical ingredient in the cryptographic key business. And the reason people write it in this form, there's a nice theorem in number theory. In fact, I've seen it called the fundamental theorem of arithmetic, which sounds very profound. But it basically says if you have two prime numbers, which you multiply together to form this big number n, those prime factors are unique. There's only one pair that will do it. For example, Trina mentioned for 15, 3 and 5 are prime factors of 15, and they're the only prime numbers that will multiply together to give you 15. So that gives some uniqueness to the ingredients here. So, next question. What are the prime factors of 77?
11 and 7.
Okay.
Yeah.
Are there any others?
Nope.
No, our fundamental theorem says there should not be any others. And there aren't. I mean, you can go through all the prime numbers up to 77 and try it. But that theorem says that no matter, once you have those two that work to give you the number 77, you're finished. Okay. Another number theory issue that comes up is called the greatest common divisor, the GCD. This is the idea if you have two numbers, you can ask, are there any numbers that divide both of those numbers evenly? And if there are, which one is the largest? And in fact, it shows up so often that spreadsheets like Excel have a built-in function called GCD. You put your two numbers in that function, and Excel will tell you what the greatest common divisor is. So let's take a look at some examples there. What's the greatest common divisor of 15 and 12?
3.
Any other possibilities? That's it.
So far,
Okay.
the chat just says 3.
Yep. Okay. What about 14 and 15?
Common? No.
Anything in common?
1?
No.
Well, 1, the number 1.
Yep.
Right. And that lack of having a common divisor bigger than 1 turns out to be an ingredient which shows up in many of these, in some of the algorithms we'll be taking a look at. So, okay, so that's not too bad. Now it gets bad. There's another function in number theory, which at first sounds kind of, if you haven't seen it before, it sounds kind of mysterious. Oh, I've just some general thing about the scheme here. is that we're going to be using prime numbers. I forgot I put this slide in here. We're going to be using some prime numbers to create these large products, and then we'll use those to develop the cryptographic keys. So the function I wanted to introduce is called the mod function, sometimes called modulus or modulo. And it's written in many different forms. The one that Alice and I have used in our book is the one that's expressed in this line up here. And what it does is, suppose you have a number x, and you want to divide it by some divisor, capital N. X divided by n may not go evenly. There's usually a remainder left over, and this modulus function gives you that remainder. Okay. And you could also write it out this way. The number x is some other integer times n. That's the part that goes evenly, plus whatever is the remainder in that particular division.
That looks like some of our physics equations.
Pardon?
That looks like some of our physics equations.
It has that flavor, but these are all just integers and are not general numbers or electric fields or anything else. This, again, occurs so frequently that spreadsheets like Excel have a mod function built in. So you just give the divisor and the dividend, plug that into the mod function. It gives you the remainder over here. But let's try a few out here just to see how this goes. Oh, but I wanted to ask Alice, what time is it?
1:40.
Where did that one come from?
I took the modular. So how about military time? It's 13:41.
13 military time, but we normally use the mod 12 function to get the time afternoon. So we use this every day. Okay. All right, some examples here. And let's give 20 seconds for each one to figure out before we get an answer. So the dividend is x equals 15. The divisor is 4. What's the remainder? That's an easy one. Well, 10 seconds.
People are saying 3.
3. Okay, great. What if we change the dividend to 19? What's our remainder? Okay.
They're saying 3 again.
There you go. So this is an important point. There are a variety of numbers that, when divided by n, can have a remainder of 3. Mathematicians say those numbers are congruent modulo n. And that means they have some number theory properties in common. Not that we're not going to be using those, but you may hear that terminology being kicked around with these things. Let's try another one. Okay, not too hard. What's the remainder here?
I am looking at a couple of zeros in the chat.
Oh,
Okay.
That doesn't mean you are a zero, people who have replied.
All right.
Come on, Keith.
Oops. So hang on a second.
What's fun about this, I remember usually in math class, right, we want to know like what the answer is. And so for the last one, the answer would be 6.
Yeah.
But in this case, right, we're after the remainder. So
Yeah,
it's,
we're not after the quotient. We're after the remainder.
yeah,
That takes a while to get your head wrapped around that one, too.
yeah.
So this turns out to be 0, of course. And in that case, we say n divides x evenly. The remainder is 0. That comes up. Okay. One more.
I got it. Oh. Hmm.
Hmm.
We have some disagreement on this one, Bob.
Oh, good. We can arm wrestle over this one. Okay. Well, what happens if we do take 7 and divide it by 17?
There is no remainder.
Well, what's the quotient? Let me just back up. Let's go to this expression. So we have 17 here, 7 over here, and 17 doesn't go into some given integer, so you have a quotient of 0. So the remainder is the number itself.
It's going to be, so 7 is the remainder. Is that
Yes.
what you're saying?
That's what we're saying. In the modulo arithmetic.
Okay.
Yeah, we have to remember, we have to play the game the way the mathematicians like us to play the game. So if the dividend is less than the divisor, what remains after trying to divide that is just the number itself.
Gotcha.
Okay, get a little different, and that's why I'm just taking a look at that. All right, now here comes another variation on this modular function. We'll still have a divisor over here, but in place of just a simple number here to be divided into, we're going to have a number which is written as an exponent. So we'll have an integer a, and we'll raise it to some integer power b. Why you would ever want to do that? If you're not familiar with this, it sounds crazy, but this turns out to be extremely important in these cryptographic schemes. And we'll see an example of that in a moment. So, question I want to ask you is, suppose you choose a capital N, you choose an A, and you let B be a variable. So as B varies, what does that remainder look like as a function of B? So just think about that for a little bit. Let me just remind you that if you have a positive integer here, raising it to a positive integer power, this whole thing here is going to get bigger. Right? We have 5 squared, 5 cubed, 5 to the 4th, so on and so on, getting bigger and bigger. What happens to the remainder? Does it do anything interesting? Or do you just have remainders?
Does the remainder get bigger and bigger?
Remainder, well, or
Not
not.
necessarily.
Not necessarily. We saw one place where the remainder was smaller than.
Yep.
So let's take a look at this. I made a little graph over here.
Ooh.
Oh, this function, modular exponentiation, is not available in most spreadsheets because these numbers get big fast, and your poor, simple Excel spreadsheet chokes when you get too many digits into it, because you really have to deal with these as integers, keeping every digit in the integer. Even if there are 50 of them, 100 of them, you have to keep every one. So here's what this looks like. On this graph, I've plotted the horizontal axis is this exponent b. I happen to run it from 0 up to 50. On the vertical axis, I plot this function, the remainder, and you can see the remainder doing all sorts of crazy things here. Okay. But there's some interesting features to this remainder. It looks just sort of kind of random, but if you zoom in on, let's say, this pair of dots right here. Really high one, next one's not quite so high. That pattern is repeated down here.
Mm-hmm.
And so I've gone from about 20 up to 50. If you go 30 further downstream, it appears again.
Mm-hmm.
So this function is periodic in this exponent. And people call R little r the repetition period for that. And the little r in this particular example is about 30.
Bob, if you go down, not necessarily the highway, but you'll see another pattern right in here. I
Yeah,
know you
there are all sorts
got
of, there's a
20.
pattern. I'm sorry. Go ahead, Trina.
Okay, what I was going to say is that there's another pattern here, and then there's one right here.
Yeah. I can't see where you're pointing.
Yeah,
So,
well, it's at the 40, all across the 40. And you
yes.
see there's one goes down, then there's a high one, and then a low one. And then
Mhm.
you go down just a little bit above there, over almost to the end on the right-hand side.
Right.
It's that same pattern, 2 low, 1 high, and 1 down.
Right. So that period shows up
Mhm.
no matter where you start here. For example, this dot here reappears over here,
Yeah,
pointing out something around this area that shows
yep.
up over here in that area. And so it is periodic. Who would have ever thought about that? That's crazy.
Somebody who had nothing else to do.
Yeah. And so this is kind of a really interesting property, and it turns out to be the key part of the critical machinery which is used in the cryptographic analysis using these prime number factors. Now, if you want to try to calculate this, I say if your spreadsheet has this function, it can't go up to more than about 10 or so before it chokes. So that's not very interesting. But on the web, people have a power mod calculator, a modular exponentiation calculator. You plug in your numbers, click on a little button, and it pops up with the answer for you. And that they can do this because there is a scheme, which is a simple algorithm, iteration algorithm. It says, give me these numbers, do certain things to those numbers, and keep repeating that until you get to a certain point. That little algorithm will generate this remainder for you. There's a scheme out there for doing it. And if you're into more sophisticated computer programming, like Python has this built in, Mathematica, MATLAB, packages of that sort have these things built in to do the work for you. But again, if you're on your desert island, there's a way of going through a little algorithm by hand that gives you the answer perfectly well. Okay. All right. So now we're ready to look at this RSA algorithm itself. And we've talked about the ingredients that go into this. And in our book, Alice and I have broken this up into 5 steps, and we use Alice and Bob because everybody uses Alice and Bob in cryptography. And let's just go through the steps, and then we'll go through a numerical example to show that this scheme actually works. Now, why it works is not so obvious, but in fact will work. And let's see how this plays out. So Alice wants to create some really big number, capital N. And so she chooses 2 fairly large prime numbers, P and Q, multiplies them together, and you get this big number, capital N. So P and Q, in the language we used before, are the prime factors of this N. And then Alice chooses another number, capital K, which is less than N. And that's going to be her actual encryption key, as we'll see in a moment. And you want to make sure that, for reasons that we'll mention as we go through the example, you want to choose a K that has no common factors other than 1 with another combination of factors, your original P minus 1, your original Q minus 1. Oh, this sounds crazy. Why would you do that? We'll see where that goes. But to make sure there are no common factors other than one, we go back to our greatest common divisor procedure that we mentioned before. And again, you can just use Excel or something like that to get that step. Then Alice sends these both n, this big number, and her key number, capital K, she sends that to Bob, and they can be sent with a banner hanging out behind an airplane for everybody to see, because it turns out that those are not sufficient to know how to unencrypt an encrypted message in this scheme. But she keeps the P and the Q, the prime factors, secret because they are the key numbers to deal with in the unencryption part. Oh, okay. All right, now Bob has this information. He has capital K and capital N. He has a message, and again, we're dealing with just positive integers. So he's going to choose some integer, which will represent some kind of message. And maybe there's a code book where when Alice gets that integer, she just looks in the code book and says, oh, we're meeting for lunch at this particular restaurant on Thursdays at 1 p.m. or something like that. But the
Important
message in
message.
this game, it will just be an integer. Or it may be an integer, which is like some of the examples we looked at before, something that could be lined up with some letters in the alphabet and then becomes a meaningful message that way. But it doesn't have to be that. So how does he calculate this message? Or what does he do with this message, this integer he has chosen? Well, he takes the message he has chosen, raises it to the power capital K, which is what Alice had sent him, and takes that modulo this capital N, which Alice had sent him, to get another number, C, the remainder, which he's going to send off to Alice. And this again is our modular exponentiation. Never get those words out right. Modular exponentiation maneuver, which again, you have to have Python or Mathematica to do that, or this little simple algorithm that I mentioned, but we're not going to talk about today. So he calculates this remainder, little lowercase c, launches that off to Alice. And in the meantime, while she's waiting for Bob to do this work, Alice calculates another integer, little lowercase d. And this lowercase d satisfies another modular exponentiation function. But now we want to find out what this number is. So if the remainder turns out to be 1, we'll see why we're going to look for 1 when we get to our example. So this is using this modular stuff in a slightly different way, and this is called a modular inverse in the mathematical trade, or sometimes the inverse modulation function or inverse, a whole bunch of terms used for this kind of thing. And it's called inverse because K and D together somehow conspire to give you a 1 over here, but it's not just K, can't just take the 1 over K to get what you might think would be an inverse, because these all have to be integer numbers. 1 over K is not an integer. Okay. So anyway, whatever you want to call it, you want to find the integer little d that gives this remainder 1 when you take this mod function with this p minus 1 and q minus 1 combination that I mentioned before. That's this thing that Alice checked on up here. And having no common factors is critical to make this particular function work properly. That's why she did this greatest common divisor check. So she can do that. And again, modular inverse is in Mathematica or Python. So it's not not something you have to have in your pocket calculator. And then, so she gets this little lowercase d. So then she receives the message or the this integer c from Bob. She puts it into another modular exponentiation function and calculates a number, which turns out to be the message that Bob wanted to send. So she has now figured out what it is that Bob decided to send as a message by making use of the little d she calculated, c that Bob sent her. This d that she calculated depends on this p minus 1 and q minus 1 as part of the secret stuff that she has kept to herself. Bobby doesn't know this, and nobody else knows it. And so she can carry out, only people who know what P and Q are can decipher this to calculate the D, which allows you to unencrypt the message. Whew. Okay. Mysterious things going on. And why it works is it's moderately tricky to figure it all out. But let's first go through an example to show that, in fact, it does work. Trina, do you have a question?
Bob, number 5 is not visible on my screen.
There is probably not much I can do about that.
Okay. Okie doke.
It'll show up in the next slide.
Oh, okay.
Okay. Okay. Whoops. In fact, the last 5 turned into a 4
Oh,
here.
there it is.
Sorry
Oh,
about
something.
that. Okay.
There
So
it is.
we just
Okay.
repeated the steps here with somehow this didn't automatically increase the numbering here. But this is what was at the bottom of the previous one, Trina. Okay, so let's just repeat the step, and then over here on the right, we'll go down through a numerical example.
Okay.
Okay, so Alice has to start off with generating this number, uppercase N. So she chooses 2 prime numbers, 59 and 47. Doesn't matter too much what they are. And for this example, I use modestly small prime numbers. In the serious cryptographic business, people use things with hundreds of digits for these prime numbers. So
They would.
and then you get a really big capital N number, but it's easier to see what's going on with more modest sized numbers. Okay, so she's chosen those, how it's calculated capital N. And then she calculates this P minus Q minus 1 combination. That turns out to be 2,668. And she wants to choose a K that has no common factors with this number. And she decides to choose K equals 17. Choose whatever she wants. Checks with the greatest common divisor. The by hand algorithm is called the Euclid method. So Euclid, way back in the Wayback time, had worked this out. It was among his geographic enterprises. He also did a lot of stuff in arithmetic. So we have the Euclid method. You can do it by hand, but you check that the greatest common divisor between the 17 and 2,668 is 1, which in fact works out. So she ships off the K and N to Bob, keeps the P and Q to herself. And so Bob has to decide what his message is going to be, chooses the integer 73. I don't know what that means, but that's the message he wants to send. And so he goes through this exercise of modular exponentiation. You take the capital N number, put it in here. You put in your message, 73, raise it to the K power, which is 17. And of course, everybody knows that turns out to be 928. Well, that's a little whimsical. You don't know that, but you can calculate, again, Python or Mathematica will calculate that for you with no difficulty whatsoever. So this number C is what Bob then sends off to Alice. Now, if somebody happens to intercept this C on the way to Alice, they can't do anything with it because they don't know this P and the Q, which they need in order to do the next step in the unencryption process. So at this point, this is just a number 928 that Bob is sending to Alice. So Alice now needs to calculate this lowercase d using this inverse modular function. And again, you can do that with Mathematica or Python. And it turns out lowercase d in this case turns out to be 157. Not so obvious, but you can check it easily enough to, once you have it, 17 times 157, take that as the dividend, 2668 as the divisor, and you want to get a remainder of 1, and that all works out if d is 157. And then Alice takes that little lowercase d, does another modular exponentiation with that. Here's a 928 raised to, that's the lowercase c, raise it to this power, take that modulo, the capital N that you started with, and that turns out to be 73, the message that Bob wanted to send. So the message got through. Bob chose that number, did the encryption over here. Alice did the unencryption down here and retrieves that number 73. And unless somebody knows what P and Q are, there's no way for them to know what lowercase d is going to be. There's no way that they can use that last step to do the unencryption. So we should all pat ourselves on the back. We've got our way through this. Now, so numerically it works. Now, the deeper question is, why does it work in terms of all the number theory? And that's a much more complicated thing to get into. We'll give you a reference at the end that gives you a lot of the details for that. Or there's a nice Wikipedia article, which also gives you some of the details, plus some examples of how the RSA algorithm has been modified over the years. So let's just pause. Anybody have any comments or questions at this point?
Joe says number theory crops up in calendars, and I've always found it rather difficult.
Yeah, it does some mysterious. Each step of the operations is maybe a little mysterious, but you can sort of see what's going on. What is challenging is putting the sequence together to carry out a task, and that's where RSA get the credit for figuring out how to make this thing work. And it turns out the history of it, that they bobbled it the first time and had to go back and reconstruct it to make it work appropriately later on. So it's not so easy to do. And these are 3 MIT mathematicians working many, many hours to try to make this thing go.
We have a question about whether we need large prime numbers to make this work and to make it secure.
Yes, because you're distributing publicly this number capital N, if you can find the prime factors of it, that's the P and the Q, then you know what how the game is played, then you can break the code because you know the ingredients to get to this letter D. So, but if you make this big enough, it becomes extremely difficult to find those prime number factors. I did a little estimate for our book which says, if you have something which is maybe something in the order of 200, 300 digits for capital N, and you can do check. Have to do is check all the prime numbers up to that number. There are something like 10 to the 150th power prime numbers up to that 300-digit number. And if you do that every 10 nanoseconds, it takes you 1 billion times the life of the universe to carry it out with our fastest computers today, all of them churning on the same problem. There's no practical way to do it. So that's why people like these prime number schemes. But what we'll see in a moment, there's a quantum way to do a lot faster. Anything else? Okay, a little wrap up here. So just a summary, to crack that code, you have to be able to find those prime factors with a lot of bits in those numbers. It's really impossible to do for ordinary computers. But there's another algorithm called the Shor algorithm, which says, okay, we can be clever now that we know about quantum mechanics to find a way to do it, factor these numbers much faster. And the Shor algorithm just runs that whole process backwards, making use of the same modular, I won't go through the details, but modular exponentiation in a particular form. You get this particular result here, that this number A raised to some power R, which is the repetition period for that modular exponentiation, I'm sorry, has to give you 1 here, bring the 1 over the left-hand side. You have something which has to be evenly divisible by some integer multiple of this big number n. You can factor that into 2 parts, which have a -1 and a +1. And from this, you can then figure out the P's and the Q's by a greatest common divisor step. So if you can find that repetition period, you can crack the code. And what Shor did was to show you could use the quantum Fourier transform, which we're not going to talk about. It's another 2-hour workshop. Quantum Fourier transform. It's just a quantum version of the Fourier transform that we all love so dearly. But it makes use of superposition states and good quantum tricks of that sort to speed up the finding of this period, little r, and so it can be done in a finite period of time. But it takes a lot of qubits in a super big quantum computer, which we don't have yet, to actually carry this out. But the fact that it's possible is what is keeping the cybersecurity people awake at night. And so if you can do the Shor algorithm, there'll have to be other ways of doing encryption, or alternatively, and this is going to be the next part of our discussion, we'll have a way that you can detect if somebody is looking at your communications channel. And if you know that, then you can not worry about whether that can be encrypted or not. You just change the message around and avoid being unencrypted that particular way. So that's the end of what I have to say. We're going to bounce back to Alice, but I had suggested we take a quick 5-minute stretch break so we can all just move around and move arms and legs a bit. And let's reconvene at 2:18 Eastern. Okay?
Sounds great.
Good. Ding, 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 ding. Okay, now we get to the fun physics part. A little less math theory, hopefully. And we're going to use polarized light. Let's see. Let me see if I can move people's faces out of the way so I can see what I'm doing. Okay. So, you're all physicist, and maybe you teach polarization with the picket fence analogy. This is a picture from the physics classroom, and this is the wave model. So just to be sure, to make sure we're all on the same page, if the oscillations of the wave match up with the, are they called pickets of the fence, the wave will get through. But if they're 90 degrees rotated, they will not. Okay, and that's, most people tend to think of polarization in terms of the wave model. All right, but what about if the polarizer is at an angle? And however much polarization you teach, classically we do it with vector components, and it's Malice's law. And you can think in terms of dot products or just geometry, but we need to have a factor of a cosine theta. So you can do this classically with waves and with vectors. To make quantum cryptography, which cannot be hacked with any kind of algorithm, even on a quantum computer, we're going to have to think about it in terms of photons. So not the wave model, but the photon particle model. Right, so it's in my class, it's a way that I can do a little more wave particle duality with them. And everybody loves cryptography, that I can actually get them to do quantum physics at the end of the year. Okay, so when we meaning Quantum for All and Physics PTRA, we worked with University of Waterloo, their Institute for Quantum Computing, and they have what they call the two golden rules of quantum mechanics. So there's a superposition, that you can be in two or more places at once, right? You can be here and there. Little brown cat kitty there. Oh, I said kitty and my cat's not here. Whoo, success. So that's the first rule, the superposition rule. And the second quantum rule has to do with when you measure something, you collapse the superposition. We could get into a lovely philosophical talk about what that means, but we're not going to. But you could change the state when you measure it. So now instead of being here and there, we have here or there. So basically go with rule one, but if you measure it, rule one does not work anymore. So looking at this in terms of polarization, little roundy guy, here's my photon, here's my polarizing filter. So it doesn't match up. So before it's measured, it is in a state of superposition. Okay. Relative to this measurement basis, it is in a state of superposition. And it'll be probabilistic about whether it goes through or not, right? Photons can't be cut in half. So it's either going to be not go through or go through. So once we let it interact with our measurement device, we could have it not go through and be absorbed. Or we could have the whole thing go through, but we have now changed it. The information we have from the measurement is in the measurement basis of the polarizer. Okay. We don't know what it was before. Humans can't see polarization. But after, we get this. We don't have any information about what exactly it was. And that's going to be important later on. So I'm going to show you this handy dandy sim. So this is Quantum Atlas. And they have a whole bunch of fantastic quantum sorry, I just read Joe's comment in the chat. A bunch of fantastic quantum resources. Okay, so it's worth checking out if you are interested in quantum or teaching quantum, but they do things with photon polarization. Okay, so what do we got? The only complaint about this, I can't stop it. Okay, so changes we want to make. So let's go for having them line up. Okay. No surprise in there, I get 100% transmission. If I change this to 90, okay, I get no transmission. Okay. Thanks, Chris, for putting in the link. And then what if we do that 45 degrees? You see, some of them get absorbed. You cannot predict which one will get absorbed. But ones that make it through now are in the measurement basis. The information that it was originally vertical is lost. And if we let it run fast enough, we'll get to the 50% or so. Okay, cosine of 45 squared. So this is a great way to introduce students to the idea of the randomness in quantum. And you get the same results as you do classically. But it also gets them used to working with photons, which they probably haven't done before. We're interested in sending messages. So we have to be able to map on our photons to binary. You all know, I'm sure, that there's the ASCII code for your keyboard. Every letter, every symbol, capital letters versus small letters, have a binary digit that goes along with them. So we can send messages with binary, not just a number. Like, what was your number? I think, Bob, you were 73. We can send letters and things, but we have to map them onto a photon. So if I'm going to be looking at the horizontal vertical basis, so my polarizer is either going to be horizontal or vertical. I have a horizontal and a vertical photon. Horizontal could be 0, vertical can be 1. Doesn't matter what you choose, as long as you and Bob agrees with it. Okay, and then we have the same for the 45 basis. And these are the two that, at least for us education people, these are the two that we tend to use. There's nothing magical about these. 45 is nice because then it gives you that 50% probability. It's a nice, easy probability for students to work with. But what if I have my horizontal photon with a 45 basis? Or what if I have my lovely 0 here with the HV basis? Well, now I have superposition. And I have the magic of quantum. So it's going to randomly determine what it is. It may go through, it may not go through. But if it goes through, again, the basis, it's going to assume characteristics of the basis that you measure. Again, I'm making a big deal out of that because that's how we're going to catch an eavesdropper. Okay, so let's go through the BB84 protocol. There's a bunch of different ways to do this. And so if you're interested in a more like hands-on, we've developed something with bingo chips and things like that. We're going to do it with, what are we going to do it with? We're going to do it with spreadsheets. There's also a computer site that I'll tell you about. So this is actually we'll start off with the computer site. So this is the St. Andrews QVIS site. And I think I will have the address for you. If not, Chris will work some magic. Okay. So kind of what we did before, if in your chat, in my chat, our chat, could you tell me something that you see there? All right, let's see what we kind of explore this picture a little bit. What do people see? Hopefully you see Alice and Bob, but what else do you see? There's a kind of a lot of information on here. Ah, we see some Dirac, yes. Even though you don't need to work with direct notation to do this, it's nice to bring it in, get people a little bit familiar with it. Okay, we do see two different polarizers. Alice has one, Bob has one. And can you look at when the key is made? Okay, now that we've seen that there are two polarizers, I gave you two examples on the screen. One where there is nothing with the key and one where there is something with the key. Can you figure out when there's a key? And I'm gonna figure out what is wrong with my cat. Oh, I see what's wrong with my cat. Okay. Oh, nice. It filters at different angles. Any other ideas about the key or anything else you see in this picture? Oh, wow. 403 forbidden. I'll see if I can find a site. Maybe that's weird. I've never had that happen. Somebody doesn't like where you are. Okay, so now you see an overview, right? We have Alice and Bob with different polarizers. Okay, Alice has one, Bob has one. We have these two different bases, 45 and HV. Sending polarizers. Alice is preparing a photon in a polarized state. Bob is going to measure it. In this case, Alice has a different basis than Bob, and there was no key. But in the bottom one, Alice and Bob had the same basis, and we got part of our key, right? We don't want a key just to be one number. That's not very secure. It could be 0 or 1, right? So we would have a whole series possibly of thousands of them. Okay, so why do we only keep the bits where the bases are the same? What's magical about that? And refer back to the golden rules. When we had a horizontal photon with the HV basis versus a horizontal photon with the diagonal basis, this basis, you were in superposition. And because you're in superposition, you have an uncertainty. The result will not be consistent. We want to make a key where Alice and Bob have a consistent read on it so that if I get my photons and I'm sending enough photons to make a key for 010101, I want to make sure Bob is going to be able to get that same key. So I'm going to want to only keep the ones where our measurement basis and our preparation basis are the same. Okay, so again, we don't want to deal with superposition. So how does this work? That's why I always say Alice has to do all the work. Unlike I think a lot of our writing, Bob. So I need to prepare a photon. So I'm going to choose a 1 or a 0. I'm going to choose a basis and a photon direction to encode that bit and generate the photon, send them over to Bob. Bob has to decide how to measure them. And of course, humans can't see polarization, so we have to have a detector. When I do this with students, and we do a little bit of role playing, I have an Alice, I have a Bob, and then I have a detector, so that it mimics what is it that the humans get to see versus what you don't. So I'll show you the spreadsheets that I use in my class, and I'll give you a link to them. So here's Alice. So the way this is set up, you can choose the first 10, and after that, it does the rest of them, 90 of them automatically with a random number generator. You choose the basis for the first 10, 90 more get done for you. And then it will automatically encode the photons for you. So it's kind of, this is a quick way to do it. So we have Alice. Alice has now sent the photons to Bob. Bob has to choose measurement basis. Same thing. Choose your 10, The rest of them will be done for you. So what are they going to share? Because again, this is public key distribution, public. Just like when Bob was talking about the RSA and Alice publicly sent the N, not the P and the Q, but the N and the K. Alice and Bob will publicly say what their bases are. Alice will say, hey, Bob, for the first one, I use the diagonal basis. And Bob would say, me too. And they'll just keep doing that, keep doing that, keep doing that. And that's all they have to share. They're not sharing what the photons were, and they're not sharing what the bits are. And they don't have to. Alice knows she sent a 1 with a photon for that basis. So she sent this orange photon here. Because Bob used the same basis, she knows he also read a 1. So they know that if they have the same basis, they know they ended up with the same bits. But again, sharing the basis doesn't tell anyone whether it was a 0 or a 1. And if you have a long enough key, it's going to take a long time to figure out all the different permutations of what that 0 and that 1 would be. So the way the spreadsheet is it'll highlight when they have the same basis in one color and a different basis in another one, so you can see what the key is. So this is kind of an easy way to do it. It's a quick way, and the students can actually kind of do it themselves. Okay, so any questions before we talk a little more about this? And I will see what I can do to get you the spreadsheet thing right now. And Chris, you couldn't get to QVIS, correct? Or was it the Quantum Atlas?
No, it was QVIS. Okay, it's just me.
Okay, that's weird. Okay, so I don't see any questions. So let's finish up here. Okay, so it's unbreakable because of what's being shared publicly. It's also unbreakable because there's no pattern. That element of superposition, so that you get that randomness, works as long as the humans behave. Okay, we want to make sure that Alice will randomly choose her basis. Okay, and not have some kind of pattern. Another way is that they were solving the enigma is that some of the operators, when they were sending things, they were using their girlfriends' names over and over again and things like that. So the human part, quantum cryptography does not solve. But as far as patterns like traffic analysis and frequency, it can solve, as long as you embrace the randomness and make sure things are as random as possible. And by the way, just so that, remember, this is only the key. We still have to send a message. So the way you can do that is with the exclusive OR. So you use exclusive OR to add your message and your key together to get your cipher, what you're going to send to your receiver or your Bob. And then Bob has to just do the same thing. Adds the cipher and the key using the exclusive OR, and we'll get the message back again. Again, emphasizing, because my students get lost in what we're doing. We're only getting the key, not the message. Okay, then this advantage about Eve. It's funny because the students who really get this are the ones who read spy novels. So they understand that if you're going to eavesdrop on a message like this involving photons, if Bob doesn't get any message, Bob knows that they were intercepted, and Alice and Bob know that their information was not secure. So the eavesdropper, Eve, needs to send photons on to Bob. She can't just read them. But in order to measure, Eve doesn't know what basis Alice used. She has to choose one just like Bob chose one. The photon is destroyed, and she needs to send a new photon in her basis. All the information she has is from her basis. Okay? The prior information is not accessible to her. So what happens if Eve's basis is different than Alice's? So let me see if I can get some action in the chat. Okay, just tell me if Eve's basis is different than Alice's, can Bob end up getting information different than what Alice sent? A simple yes or no. If you want to go for an explanation, that'd be great. Okay, but if Eve's basis is different than Alice, is there a chance that Bob's going to get some different information? Yeah, right. So Bob's going to get some different information. So in order to catch an eavesdropper, we got to do a little bit more. Okay, and as far as the rules, right, we're doing the measurement. We're focusing much more on that rule to catch Eve. Okay. So you guys had already nicely answered that question. So I'm going to skip this one for a little while. And Chris, do we send our slide decks, right? We have a way to, or should I put a link in the chat at the end?
We can post it on our website if you send me
Fantastic.
the link.
Okay. Okay, so remember when we were just doing the key distribution, they were just sharing basis. They never shared the bits. If you want to catch Eve, you need to now look at a subset of the bits, right? These keys are thousands of bits long, maybe hundreds of thousands. You're just going to share a little bit and look for changes. Now, quantum, systems have some noise. So if only one out of your, 1,000 or so is off, maybe you're not too concerned. But if you're seeing several, you're going to probably scrap that key and try again a different time, a different place. So what does it look like with the St. Andrews? I also, on the spreadsheet version, there's also an Eve version in that same folder. But this one's prettier.
Alice,
Yes.
there is a problem with the spreadsheet link. It doesn't seem to work.
Okay, I will look that one up too.
All right, thanks.
Okay, yep. Okay, so here's what it looks like. This is the qubits like before. Now we have Eve in the middle, right? This is kind of what I asked you to look at before, right? So we have Alice, and Eve has to choose a basis, right? She has to detect it also. She has to prepare another photon to send to Bob. Okay, so we're going to have Alice and Eve and Bob, lots of basis. By the way, on the qubit, right, there's a button for you to push when you want Eve and when you don't want Eve. Okay, so take a look at this. Alice and Bob both use the same basis. They should have the same results, but they don't. Because Eve was in the middle. Eve chose a different basis. Even though she ended up finding the same bit as Alice sent, but now Bob is measuring a diagonal photon with his HV basis, there's a probability it's going to flip. It's not going to be the same. And it worked in this time. It worked in that they caught Eve. Okay. So there was an error and they caught Eve. Sometimes Eve does get away with it though. Okay, so here's one where she gets caught. This is the same one I just showed you, right? Alice and Bob had the same basis. Eve chose a different one. The bit flipped. And when Alice is like, hey, for the first one, I said a 0. And Bob's like, oh, I got a 1. Notice, right? You only check when the bases are the same, right? Bases are the same. Alice and Bob, there should not be superposition. They should get the same. But with this first bit here, even though Eve chose the wrong basis, because of the superposition of Eve's photon and Bob's basis, he still got the same bit. So in this case, Eve got away with it. So you have to check multiple bits in order to make sure that you catch Eve. And again, on the spreadsheets, there's an Eve version also. Okay, that has a whole lot of information that you can, delete a lot of it if you don't want your students to have it. I think that is the end of mine. Yes, because there was a shameless, what was that? What did you call it, Bob? Shameless commercial something or other.
Yeah.
So I will stop sharing. And I will check the link. Okay, if anybody has any final questions, or does who in the audience teaches polarization in their classes? Is that a normal thing in a second semester? Looks like a yes. Oh, that's good. It's a good thing to kind of hang your polarization to try and get students to study.
Alice, ask the question, what for someone who teaches polarization with what second semester? The question you just asked.
I was just asking who teaches polarization in any semester. I
Okay.
guess I think waves is sometimes, oh wow, yeah, that does not work. I'm gonna get you a better link for the spreadsheets. Let's see.